I am Royce Kim, and this is the experiment on constant velocity. So the purpose of the experiments is to compare the observed position of an object traveling at a constant velocity, since no net force was applied during rolling motion, with the predicted position calculated from the computational model. This experiment demonstrates Newton's second law. The object is whiteboard marker, the observation is held by tracker, and the prediction or computation is done by GlowScript. The system, the object whose motion I am analyzing, is the marker, and the surrounding, which is everything that can interact with the system but not part of it, would be the hand, the table surface, the air, etc. So the Newton's second law of motion is called the momentum principle, which is the rate of change in momentum is equal to the vectorial sum of forces on a body. So since P is mv, so if we do mv final minus mv initial and organize the equation, you can get the velocity update formula. So the experiment procedure is the following. I recorded the video of a marker rolling at a constant velocity, which is constant speed, with one direction next to a ruler. And then I imported the video into Tracker and tracked the marker's position frame by frame at set time periods. And then I created the computational model of the marker's predicted position in GlowScript. I then generated a spreadsheet of the observed and predicted position and graphed the data over time. Finally, I graphically compared both models to draw conclusions. So since the video was 90 degrees rotated, I set the direction of the marker's movement to positive x direction. So you can see I made a calibration stick and I did set the axis. And since my hand covered the body of the marker, I set the tracking center to be the middle part of the marker lead. Tracker analysis. So observation start time is 0 second, and marker's initial position is following, but I regarded the initial position as 0, 0, 0 since I have considered the magnitude of each vector negligible. I then calculated marker's initial velocity like this to get the result. The initial velocity is 0.3061, 0, meter per second. And time of last observation is 0.900 second. So these are my computational model, and just keep in mind that this is a marker that I use, but to be simple, I just set the variable to be a ball. So if you check this, the net force is set to be 0, and I put initial velocity and initial position, and delta t in this case is 1 divided by 30 since the recording was 30 frame per second. And mass of the marker does not affect the velocity, so I just kept it 1, and I used position update formula to predict the location. So this is the result. So if I see the two graphs, there's blue line is model position and red line is experimental position. So we can see as time goes on, the experiment position starts to diverge away from model position. It means there is some force outside that slows down the marker. So possible errors. First can be friction. There is a friction caused by the hand, which rolls the marker, and the table surface, or possibly the air. Secondly, since the human marked the tracking center, there might be error in inconsistent center tracking. And lastly, there might be rounding error, as I regarded the initial position to be 0, 0, 0, using less precise values beyond the decimal can affect the result. What happened if you flip the axis? What if positive x and negative x were interchanged? The position versus time graph shows positive slope. This is because I set down the screen way as a positive x-axis. So if I interchange positive x and negative x, then I would get negative slope, but the absolute value would be equal. Is the net force 0? Can we calculate how many forces are being added together to give this net force? As you can see on two-line graphs, the computational model, which is blue line, overestimated the position of the marker at greater time interval. It indicates there are other resistive forces at play that did not give the system a net force of 0. I could guess that friction caused by the air and our table surface or possibly my hand affected the result, but I cannot accurately calculate the number of forces added together in this situation. Thank you for watching this presentation.